So I'm delighted to welcome Scott Archer-Nicholls from the University of Cambridge to talk about the redefining the standard for the CRI-Strat scheme. So thank you, Scott.
Thank you, Luke. And could everyone see that? Just thumbs up. Great. Okay. So hello, everyone. Yeah, as Luke said, I'm a postdoc at University of Cambridge. Been there for a few years now. This is kind of sort of the main thing which I've sort of done whilst at Cambridge. Biggest piece of work anyway, which is implementing a new chemical mechanism into the UKCA model. The mechanism is called CRI-Strat, Common Representatives Intermediate Scheme, with stratospheric chemistry, which I'll be talking about a bit more. I did this course probably about 6 years ago now. Was that when I first started at Cambridge, 5 or 6 years ago? And then I've actually taught on it most years, but just haven't had the time to this year, unfortunately. But I hope you've been enjoying it. I think this, a lot of how I actually did this development is based on the kind of stuff that you've been doing in this tutorial. So I think this is quite a good a way of showing how the tools which you are learning during this course can be applied to improve the model and do some interesting science with it. So yeah, just to thank Luke for putting this on and for inviting me to talk here. James is also going to be giving a few slides at the end because he kind of followed on with what I started and built on it. And yeah, thanks to all these other people here who have helped along the way with this work. So in terms of what we're sort of interested in here, this development is really trying to improve the representation of tropospheric chemistry in the UKCA model. So as a sort of like rough overview of the kind of processes that we're interested in, you've got these emissions from various sources like agriculture, anthropogenic emissions, the biosphere, wildfires, volcanoes, shipping emissions and sea emissions. And these will emit lots of primary pollutants such as carbon monoxide and sulfur dioxide and volatile organic compounds. And these get processed in the atmosphere to things like sulfuric acid, or they can form ozone and form particulate matter. And then the secondary pollutants can become affected around. They can affect things like cloud formation, cloud optical properties, or they can contribute to the greenhouse effect, or in some cases offset the greenhouse effect. And it's sort of understanding this, the composition of the atmosphere, particularly these sort of short-lived pollutants, can be quite computationally intensive, but these can have like quite a dramatic effect both in terms of air quality and on climate. And because there's sort of so many species and so many reactions going on in the real atmosphere, it becomes necessary to simplify it when you're running it in a 3D model. So a sort of very simple overview of like how you form catalytic production of tropospheric ozone. You have VOCs going in. These can get oxidized, usually by the hydroxyl radical, and to produce RO2 and HO2 radicals. These will react with NO to form NO2. And then if the NO2 is photolysed, that will produce ozone. And this is the primary source of ozone in the troposphere because obviously you don't have shortwave photons that can directly photolyze molecular oxygen. So OH radicals can oxidize VOCs. So methane is kind of the simplest example of that. It'll form a methyl peroxy radical, and then the methyl peroxy radicals react with NO, as we just said. In a sense, ozone is a byproduct of these VOC oxidation reactions, which are catalyzed by NOx. So if this happens without NOx, then that actually causes net ozone loss. But when it's when you have a sort of happy mixture of VOCs and NOx, you can get very efficient ozone production. And a classic image of how this looks like is these sort of ozone isotherm plots, where you can have these NOx limited regions where there is lots of VOCs but not enough NOx, and you don't have enough, don't produce ozone. And then these regions in the top left, where you have VOC limited, so there's lots of NOx, and that actually increasing NOx in these cases will decrease ozone. But when you have, if you increase both VOCs and NOx at the same time, then you'll have greater and greater ozone production. And this actually makes it quite tricky from a policy perspective in terms of, if you're in this regime here, actually reducing emissions of pollutants like NOx will actually increase ozone locally. So it can become quite a difficult problem. The thing is, though, is that this sort of summed VOC emissions that we have here along the x-axis, that's a great simplification of reality. So there are thousands of VOCs which have been identified in the atmosphere, and there's practically infinite combinations of different isomers that you can have in reality. And so in order to deal with this, in a typical transport model, you're probably looking at 100 or 200 transported species tops, and a few hundred reactions. And so you have to massively reduce the complexity of it in order to be able to run it in a 3D model under a reasonable time frame. I like this kind of image here. This is Tracy Emin and her Turner Prize winning bed. If that's what reality looks like, this would be a typical model. It's a gross simplification. And as that famous truism goes from George Box, essentially all models are wrong, but some are useful. When you're thinking about this stuff, you always have to make big approximations. The question is whether the approximations that you're making are suitable for the scientific questions that you're trying to tackle. And often more complicated or more realistic doesn't necessarily mean better. You want to try and have the optimal level of complexity for the scientific problem that you're trying to tackle, or whatever issue you're trying to tackle. So in terms of how the CRI mechanism was developed, it probably helps to sort of think about how most chemical mechanisms get developed in practice. And so I'm using here the example of strat-trop, which is the stratospheric and tropospheric chemistry mechanism that is the standard that we use in UKCA. And the way this gets developed is that there are various fundamental parameters which have been derived from accumulations of lab data and kinetic experiments, things like different rate constants, and scientists will take in what they think are the most important ones of those reactions, what are the most important species, what are the key reactions, to develop a sort of chemical mechanism. And there'll be various sort of steps that you can use to sort of simplify that in this process. And then you'll put it into a 3D model and you'll evaluate it against, your observations that you have. And over time, there'll be various ad hoc updates. Often this comes by people discover a new piece of chemistry and they think it might be interesting. And so they add it to the model and they take new fundamental parameters and they go through this loop again. The thing is that, what are the most important reactions that you can put into this? Often it's derived more by the interests of the scientists who are using the models necessarily than some sort of rigorous process to understand, what really does need to be captured and what doesn't need to be captured. If you're evaluating against like surface sites or aircraft or satellite data sets, it's very difficult to separate any biases due to the chemical mechanism that you have from other model errors, such as the transport scheme or convective parameterizations and what have you. And you can have sort of compounding errors as the mechanism expanded. So you can have these weird things where, one version of the model gets tuned to fit the data, and then someone realizes that the chemistry is wrong, and then they improve the chemistry, and then it actually can make the comparison against some sort of observations worse. And it becomes a really almost intractable problem. There's no traceability to our sort of explicit mechanisms, which we know are sort of the best standard, as close to reality as we could sort of get. And so the common representatives approach tries to be what it calls like an intermediate complexity scheme. So it sort of sits in the middle of these very complex near explicit mechanisms, such as the master chemical mechanism, which will have, thousands of species and reactions in them. These would be based on sort of various lab studies and theoretical empirical models of rate constants, matching ratios, what have you. There's a whole series of like chamber validation to build the model, and then a rigorous process of mechanism reduction where species get lumped, but at every stage of the lumping that occurs, you test it against the whole full model, in this case, the MCM, to check that it can still reproduce the same amount of ozone forming potential. And so what you have then is that every version of CRI maps to a particular version of the master chemical mechanism. And when we say maps to it, really what we're saying is that it's given the same input of VOCs and NOx, it will produce the same amount of ozone, and it has traceability to that scheme. And if the MCM gets updated, then they can go through this process again to update the CRI. And this is just kind of a summary of what I was just talking about there. This will be like an oxidation of a single thick alkane. And what happens is that you have the same original species, but as they get oxidized, they form these little radicals species, which get lumped together based on how many ozone molecules they can potentially produce. So this would be sort of the equivalent thing in the MCN, where you have lots and lots of complex different isomers, and these isomers kind of get lumped together based on how well they can produce ozone. And we find that when you do this, you can reduce the number of species by order of magnitude, but preserve your ozone forming potential. So I originally put in CRI version 2.1, reduction number 5, which is the simplest version of that scheme, which is traceable to the MCM version 3.2. I then added the stratospheric chemistry, which is already in the model, and linked it with the GlowMap aerosol scheme to give what we're calling CRI-Strat, which is because the original CRI mechanism was only for tropospheric conditions, and we wanted to be able to run it over the whole atmosphere, so we could essentially use it instead of strat-trop if we wanted to. And you can see here that you have a sort of over a doubling in the number of transported species, and particularly you have a huge increase in the number of proxy radicals, going from sort of 9 proxy radicals to 47. But I set it up so that those aren't transported, so that does actually reduce the computational cost a lot, and you don't need to transport them because they're so short-lived. You can also see that the number of chemical reactions has more than doubled, going from 212 biomolecular reactions to 554. So this is a huge increase in the complexity. In terms of what kind of chemistry is added with CRI, you have alkanes and alkenes all the way up to C4. You've got aromatic chemistry, which doesn't exist in CRI-Strat. There's a lot more detailed BVOC chemistry, so particularly isoprene, alpha-pinene, and beta-pinene oxidation. There's a whole load of higher organic nitrates, which can be important in terms of transport of NOx. And then there's self and cross reactions for the proxy radicals. It also means that I'm able to use all the VOC emission classes from the data sets, which is something that I'll sort of talk about a bit more in a second. And so in terms of like where this sits, like we were saying, we should see it as an intermediate complexity scheme. We're not saying it's going to replace strat-trop because it is quite a bit more expensive and more complicated. And there are many scientific uses where strat-trop is more appropriate, but it can be used as a sort of benchmark for testing it against. In terms of how I went about this, I kind of can call it sort of Alice and Bob on steroids. So what you've been doing particularly in tutorials sort of 4, 5, 6, 7, what have you, but for a whole host of other species and reactions. So essentially, you add new species to the stash master file using existing species when possible, and you add the appropriate mass and conversion values for each of the species. adding biomolecular, termomolecular, and photolysis reactions for the new species into the UKCA Chem master file. Again, using existing reactions where possible, so as not to duplicate stuff. Making emission files for the new species that didn't previously exist, and codes to read the emissions. Adding wet and dry deposition coefficients for the species that are deposited. Then copied the stratospheric and aerosol chemistry as was required for it to be a full atmosphere model, test run, what have you, and eventually got there. And I'd like just to say that, the UKCA trading course exercises proved invaluable. I actually found them a lot more useful as a reference than a lot of the documentation that's for the for doing this work. So yeah, that is, I would recommend this course, definitely. This is kind of an example of some of the codes. So you have here is like the stash master. These are a load of different carbonyls that are produced in the mechanism. Wouldn't worry about too much what they mean, but these sort of ones here, that's saying please use this if you're running with the CRI-Strat mechanism. And these ones here, which are in the higher numbers, so section 34, like above 872, these are all the non-transported peroxy radicals. So defined a new type, which are these non-transported prognostics, which behave like normal chemical species within the Strut solver, but are not transported. This is the initial KPP reaction files, which I've been working from. And I sort of turned all these. I actually wrote code which could read this in and write out Fortran code that looks like this that I can just copy paste into UKCA Chem master. And these, if you see it saying like CS at this point, that means that this reaction is being used in the CRI-Strat chemical mechanism. When you have these ones like this, like OH plus methane, which is in the TROP-ISOP, the stratosphere, troposphere, and the CRI-Strat mechanism. And then you sometimes have these A signifiers, which means that you use this reaction if you're running with aerosols. So if you're running with aerosols, alpha pinene can also produce some sec-org. But if you're running without aerosols, it just degrades. I mentioned the emissions earlier. So one of the difficult things that I sort of found with this was that, firstly, that CRI-Strat splits up emissions a lot more. So for example, these VOC classes, ethane, ethene, and ethine, these are all individual species within CRI-Strat, and they have their species that they get mapped to. But in Strat-Trop, all of them get lumped together as ethane. So that has a huge change to how we expect the chemistry to operate, particularly in sort of more polluted regions. But then there are also species such as the aromatics, which in CRI-Strat, these get mapped to benzene, toluene, xylene, whereas there is no species that these get mapped to in Strat-Trop, so they just get lost. And that's particularly true if you look at, say, the monoterpenes. These get mapped to alpha pinene and beta pinene in CRI-Strat. In Strat-Trop, they get lumped to this species, which is just called monoterp, which can form secondary organic aerosol, but doesn't engage in any oxidative chemistry. In fact, it's an oxidant drain. It can't contribute to ozone production. And so when you add all this together, there is actually quite a big difference in the total amount of reactive carbon which gets added to the CRI-Strat mechanism compared to the Strat-Trop scheme. So that's a tricky thing to work with there. What's going on? Next slide, please. Okay. This is just kind of showing the same thing again. You have these different emission plots for ethane, ethene, and ethine, and then these all get lumped together in CRI-Strat. And as I was saying about monoterpene emissions, they get split 66% to alpha-pinene and 33% to beta-pinene in CRI-Strat. And yeah, as I was saying, there is this big difference in terms of like how the monoterpene chemistry is treated in both of these schemes. Monoterpene just gets formed into SecOrg. There's a really confusing bit in this code where it says that there's a 13% yield, but it later gets doubled to 26%. James can talk about that a bit more if you're interested. It's a bit of a nightmare code there, I'm afraid. And I just did a very simple approximation for now, where these species will undergo their normal oxidative chemistry, but they can produce the same amount fraction of secondary organic material, which can form SOA. But in the future, we would probably like to do a more explicit scheme here, where we can have some of these species can become more oxidized and condensed to form secondary organic aerosol. That's something we'll think about in the future. And James will be talking later about sort of, other things that this can be built on with CRI-Strat 2. I mentioned the proxy radical permutation chemistry. This is one of the big differences between like how the StratTrop scheme and the CRI-Strat scheme is put together. So you have these sort of reactions like this. This is a self-reaction of methyl proxy radical. There is this development where rather than explicitly having each of these reactions, they react with what we call the RO2 pool, which is calculated as the sum of all the proxy radicals. And so rather than having methyl proxy radical plus methyl proxy radical, you have methyl proxy radical plus RO2. And you just halve the products and double the reaction rate, and it all kind of balances out. And it's a way of, the problem is that when you have 50 odd RO2 species, if you try and explicitly do each of those reactions, it becomes like an n factorial problem. This way you get to represent all of those reactions with much fewer reactions in your mechanism. And I've also added this to StratTrop, which I did on the way. And having removed the RO2 transport actually speeds up the model by a few percent. So in terms of how CRI-Strat compares to StratTrop in terms of cost, you're looking at about it being about 80% slower compared to the simpler mechanism, which is quite a bit more expensive. Bear in mind, it's sort of nearly twice as expensive, but much more than double the chemical complexity. So it's not cheap. However, as I would sort of say, is that if you can afford to do 2 StratTrop simulations for Wondleton Harrison, you can afford to do 1 CRI-Strat one. And so it does fit into this space where you could feasibly use it as a sort of benchmark scheme, where you do maybe one of those runs with your all bells and whistles, and you can use that to sort of test how it compares against StratTrop over these longer simulations. And we have been looking at doing some longer simulations. So in terms of what I'm going to show you today about how the mechanisms compare, I did 10-year simulations using nudge meteorology, using the same raw data for the emissions, mapping in the different ways as I mentioned earlier. And I did 4 experiments here. There's the standard CRI-Strat with the full speciation, there's the standard StratTrop. And then in order to test what difference these emissions make, there's one which is CRI-Strat with StratTrop emissions, using StratTrop speciation. And there's another one where I split the CRI species up. So things like ethane won't be lumped, it'll be as ethane, ethene, ethyne, but I don't include any of the higher species, such as the aromatics. And so by having these extra ones here, we can sort of test what's the difference of the emissions and what's the difference of the speciation emissions. And finally, what's the difference from adding on those extra species, which are just lost in the standard StratTrop react ones. So we have here some comparisons of surface observations of ozone around the world in different regions. And you can kind of see that there is a general increase in ozone, particularly in most of the northern hemisphere. In the CRI-Strat mechanism, you get greater ozone production going on. Possibly sort of say that there's some improvements in some regions, but in other regions it's hard to say really. Often when there are biases, say in the time series over the course of the year, you get the same kind of biases in both mechanisms, which is one of the things you often find with these complex models. So year-round increase in most regions. But yeah, in terms of whether it's better, often maybe you can say it increases the winter low bias, but then can increase the summer high bias in many regions. Hard to say which is necessarily better. There is a fairly small change in the tropospheric ozone column compared to MEMLS. But you do see a big difference in the distribution. So you see a lot more ozone in the northern hemisphere downwind of where you have a lot of production, but you have a reduction in the southern hemisphere where there is greater loss. And then this is a sort of comparison of the ozone production and loss. And so even though there's a sort of quite a similar total ozone burden, that is coming from there being a lot more ozone production, but also a lot more ozone loss. And particularly there's this big loss due to the O-singlet-D plus H2O reactions. And so there's this question of, how much of this extra production is due to additional VOC emissions and how much of that is due to the change in the chemistry. And so if you do these extra runs, we find that if you run CRI-Strat, but using strat-trough emissions, there's quite a big reduction in the ozone burden. And you get a similar story if you use, if you're using the mass. So basically the difference in the ozone burden is being made up by the fact that there is a lot more NMVOCs going in CRI-Strat. Even though these ones again have higher ozone production, you have much greater ozone loss. And actually, one of the key reasons why this is going on is because you have this a large amount of loss due to this increase in the O-singlet-D plus H2O reaction, which unfortunately is really just down to a difference in the one of the rate parameters, which just goes to show that you can add a lot of this chemistry and then one of these simple fundamental reactions can really change the picture a lot more than a lot of the detailed stuff. So this is an example of some different isopleths, and you can really see here that when there are regions with high VOC and high NOx emissions, as you'd expect in more polluted regions, you get a much more efficient production of ozone in CRI-Strat compared to the same region in strat-trop, which again is sort of represented here once you have that extra speciation of your species. And so that really does show that when you're in these sort of polluted boundary layer conditions, CRI-Strat really does have a big impact on the ozone chemistry. And perhaps you might see that this might be a strong argument for using this for, maybe high resolution or air quality simulations that you want to do with a UKCA model. But yeah, even when you do have the same emissions, you do see that there's a different distribution between these two schemes. And you also see differences in the zonal mean ozone production and loss. And so you can really see here, CRI-Strat is producing a lot more ozone in the surface and the lower troposphere, but you do have this sort of greater loss, which is kind of occurring mainly due to this change in the O-singlet-D plus H2O reaction. And so overall, we get the sort of higher ozone near the surface, but more ozone lost in the upper troposphere. And this is really just showing you that difference between the O-singlet-D plus H2O reaction, which has been kind of the bane of this, unfortunately. Looking at a few other species, you get a lot more carbon monoxide in CRI-Strat. That's largely coming from secondary production from the breakdown of VOCs, particularly due to the more explicit isoprene and monoterpene chemistry producing lots of secondary CO. So you can really see that there's a lot more CO being produced in the southern hemisphere, in tropical regions. This does improve the CO bias in some regions, but unfortunately, a lot of the CO bias is actually in these more polluted northern regions, which it doesn't help a huge amount with. So perhaps there's issues with the emissions that are going into both of the models, which we need to in order to improve some of these northern hemisphere observations. And you can also see here the sort of changes due to the CO burden, but also its lifetime from changes to the oxidant budget, so the amount of OH that there is in different schemes. And just the final little comparison here is looking at differences between NOx, NOY, and NOZ. This is actually one of some of the biggest differences in the mechanism you see here. You actually get a lot less NOx in CRI-Strat. And a big reason why is because a lot more of it gets stored as reservoir species. So because there are a whole load of different organonitrates and higher pan species and greater production of nitric acid, you can, and particularly when you have additional VOCs, you can form a lot more of these nitrate reservoir species, which you form a lot less of when you're running with the Strat-Trop emissions, because you don't have those higher VOCs available that you need in order to form those that RONO2. Yeah, there is also faster production of nitric acid that occurs in the boundary layer, which means that you get more loss via wet deposition of nitric acid in the CRI-Strat scheme than you do in Strat-Trop, which also can really affect your total ozone production. And there's one of the things is that you do see these sort of differences in termomolecular and biomolecular reaction rates. And these sort of fundamental reactions can often have quite a big impact on the chemistry. I won't go into too much detail with this stuff here. So in summary, I added this comprehensive CRI-Strat mechanism, which is a reduction in complexity of the master chemical mechanism that is fully traceable in terms of its ozone forming potential. It allows much more detailed representation of VOCs, and you get this improvement in aromatic and BVOC chemistry. And this detailed ozone production is likely to have greater benefits if you're looking at high resolution, particularly air quality applications. Admittedly, it is quite a bit slower, but it is feasible to do this as like a benchmark simulation. It doesn't necessarily improve ozone and CO against observations, but this is one of the issues that we have with complex 3D models, is that there are many other structural errors. And we could sort of say here that you can use this to sort of rule out errors which are due to the chemical mechanism, and then use that to hone in what other issues there may be in the model. Well, I think one of the sort of great real things about this is really, there is this traceability, but it also has a lot more detailed chemistry that you can then use to build on if you're looking at other applications. So we're now looking at this for looking at DMS chemistry and also more BVOC chemistry and linking that with SOA. And having all these extra species and reactions allows you to do that in a much more realistic way. It's a great potential for future scientific development when using this mechanism. And I think James is going to take over now and start talking a bit more about that and what he's been doing with CRI-Strat too. And James, you there?
Yep, thanks, Scott. Yeah, so I think the first thing to say is I was very fortunate to piggyback on the end of Scott's major changes to UKCA, and what he did was really add a new mechanism from scratch, and involve considerable changes, both to sort of things that you've already seen or will see, so things like Chem Master, the deposition schemes, stash master, and things like that, and also really digging into the even deeper into the model to look at the things like the non-transported RO2 species. And then just when I was sort of about a third of the way through my PhD, Mike Jenkin, who developed or has been a major developer of the MCM and CRI-Strat, released a new version of CRI-Strat, which has some updated chemistry. And from my perspective, that was very useful because I've been looking at isoprene and CRI-Strat 2 really does improve on the isoprene chemistry. And I'm sure those of you who knew me at Cambridge are already sick of hearing about isoprene chemistry. But for those of you who didn't, you'll get to hear it now as well. But essentially the main thing is that in strat-trop, isoprene is really a major sink for OH. And the last 20 years, modelers have been trying to understand why we see much greater oxidant concentrations in regions dominated by biogenic emissions. So places like the Amazon and Central Africa, where there isn't much NOx to make sort of anthropogenic derived oxidants. And when we run our best mechanisms, we simulate much lower OH and other things like that than observations are picking up. And CRI-Strat 2 was trying to address this. And for those of you who are chemists, certainly atmospheric chemists, this diagram on the right-hand side may make a bit of sense, but the major pathway really is isoprene reactive OH to form a proxy radical, which can then form closed shell species like the nitrate species here, or methylvinyl ketone and methacrylene and the hydrogen peroxide species, which are all sort of the standard way of doing things. But then over the last 15 years, experimentalists and theoreticians have calculated and observed the formation of other species like this thing at the bottom here in red, called a H powder, which is very sensitive to photolysis. It gets fertilized and that reproduces OH or HOX. So the bottom line is we're introducing a new pathway, which means that yes, one isoprene removes one molecule of OH at the top, but if we go down the red pathway, we get one of those molecules of OH, or in fact more than one of those molecules of OH back. So ultimately isoprene is not depleting OH by as much. So, this is really sort of quite detailed chemistry of interest to a small number of people, but it can have some quite important implications for our understanding of, I guess, sort of biogenic areas, which of course were more numerous or more widespread in the pre-industrial atmosphere as well. As well as isoprene chemistry, we had some quite important changes to some of the major inorganic reactions. So Scott mentioned O1D plus H2O, which is really, the major OH forming reaction, one of the major OH forming reactions in the troposphere. And CRI-Strat 2 had quite a different rate constant, or sum of rate constants than CRI-Strat. So that led to quite big changes in OH, particularly in the free troposphere, where inorganic chemistry sort of dominates in terms of the distribution of those species. Sorry, Scott, just go back one.
Yeah, sure. Sorry.
So this is really just, again, a bit like the table that Scott showed earlier, but it's a comparison of CRI-Strat and CRI-Strat 2 on the right. It's got the same stratospheric chemistry. As you can see, we've added 9 extra species, about 40 odd, 45 bimolecular reactions and some extra termomolecular and photolysis reactions as well. So it is by no means as big a step to go from strat-trop to CRI-Strat, but CRI-Strat, as it is to go from CRI-Strat to CRI-Strat 2, but nonetheless it is an extra sort of step up again, and it does represent, and that is represented by about a 6% increase in running time. So it's just a bit more complex again. I'll just show one one set of results. If you could just, yeah. So this is low altitude OH or OH at the last sort of, I think it's 500 meters. And you can see really that the biggest increases, particularly from a percentage fractional change, are in the major biogenic regions of sort of South America, Amazonia, Central Africa and Australia. And that's really being driven by the isoprene chemistry. But the decreases there over the ocean, that is being driven by the inorganic chemistry. We're not getting any isoprene, or we're getting very little isoprene over there. But the changes to the rate constants of O1D with water and N2 and O2 mean that actually a smaller fraction of O1D forms OH in CRI-Strat2 than CRI-Strat. So we see a drop in OH there. So again, like Scott, and I won't go into detail, but like Scott, we performed some sensitivity tests where we've sort of, rather than changing the whole mechanism, we changed just a bit of the isoprene chemistry or a bit of the inorganic chemistry, so we could try and isolate these reactions. And that's I think that's a more general skill for anybody who's going to sort of go into atmospheric chemistry modeling to sort of understand how sensitivity tests can be used. It's a neat thing to be able to do, and it can tell us a lot about what's driving what, which is always important to understand. I think there's one more slide. Yep. Okay. Cool. So I can't remember if Lou's already mentioned this to you, but this is sort of the documentation for UKCA. I wouldn't recommend diving into it now. I think finish the tutorials, but it just has a bit of extra information about things like dry deposition, or depositions to chemistry, how we set up emissions and things like that. And it's always a good reference point to go to. And in here, there's a bit more information about CRI-Strat and CRI-Strat2 and how they relate to Strat-Trop. But just in terms of how we select CRI-Strat, we change UKCA Chem is a sort of switch. No, it's not a switch. It's a selector, if you will. And we can either set it as 51, which corresponds to Strat-Trop chemistry, which is what you're using today, or 59, which gives us CRI-Strat chemistry. And then we can control whether we use CRI-Strat or CRI-Strat2 by controlling this second selector here, UKCA Chem version. If it's more than or equal to 119, we're using CRI-Strat2, and if it's less than, it will be CRI-Strat. And the final thing is, most of the all the things like emissions and the speciation between, say, alpha pinene and beta pinene, all of that is the same. It really is just chemistry that's differing between CRI-Strat and CRI-Strat2. So yeah, I'm very happy to chat later about it if anyone's doing any sort of more biogenic stuff. And Scott and I, well, mostly Scott, but we've got emissions running, I guess, we've got pre-industrial sets of emissions, we've got present day emissions, and I've now made some emissions that run up to 2100 based on different SSP scenarios. So yeah, do get in touch if you would like to chat about using those as well. And back to Scott for the last bit.
Oh yeah, I think the summary is just for the CRI-Strat2 stuff. So
okay,
cool. what James was saying about the update to the rate constants. I would actually probably say anyone who wants to use CRI-Strat at this point, I'd probably recommend CRI-Strat2, just because of the updates to the rate constants. Does improve the HOX and oxidative capacity and what have you. We are just more confident in that. It was just one of these unfortunate accidents of timing that CRI-Strat, the version that I was putting in was a little bit long in the tooth when I did, and a big update happened just when I was sort of just managed to get it all working in the model for the first time. And so luckily James came along to do that update. So as we said, it's 6% more expensive, which in the grand scheme of things, if you're running a scheme like that, isn't the end of the world. It's a similar magnitude, but you do have this big improvement in HOX recycling. But yeah, particularly if you're interested in things like VVOCs, I would definitely recommend CRI-Strat version 2.2. CRI-Strat 2. And yeah, this last bit is just that we had some papers out last year, which please go and read if you are interested, and feel free to email us if you want to learn more. So yeah, I think that's us done. So handing back over to you, Luke. And if anyone has any questions, please let us know.
Thanks, Scott and James. I see we have one question from Zhu Shang.
Hey, I don't want to be recorded, so I'm not opening the video. So I have roughly 2 questions. The first one is that it was mentioned that the CRI-Strat is somehow a simplified, sorry for drilling. It's a simplified version from MCM, and the main principle is to get a very good O3 ozone basically production, or the balance of that. So my question is, how about these organic intermediates? Are they also the agreement of the intermediates, are they also good, or they are less okay than the ozone? That's the first question.
Are you talking about, I mean, the thing is those intermediates, are you talking about in terms of comparison to observations?
The organics, like the organic intermediates, the oxidation processes of those organic precursors with different oxygen numbers.
But how good they are?
Yes.
So, as I understand it, Scott, if this is right, these aren't real species.
Yeah, they're not real species. They're like, you can't really. I don't really know how to answer that. It's
they're a construct within the mechanism to get the ozone right at the end from the emissions that come in.
They're essentially they're very, very short-lived species that represent what in the atmosphere could be many, many different species, many different isomers. And so, they're extremely difficult to measure in the first place. In most cases, you don't have good observations of them. As James was kind of saying, the main thing that you have are the closed shell species to evaluate them. So there's a bit of a sort of, even in the MCM, I would say that there's an element of a bit of a black box around a lot of this stuff. Like a lot of them, we don't have detailed measurements of their kinetics or their structures. And we just sort of, develop theoretical models to try and work out what we think should be happening. That's why you can have these sort of, like, as James was saying, these sort of quite big leaps in understanding. We know that the HOX is wrong, and we know that the observations of these H-pals, which we can't explain with the current chemistry, and so there must be something going on in the middle, which we don't understand very well. And people will develop those theories. So yeah, we hope that it's a big improvement compared to this, what's going on in Strat-Trop, but it's tricky business. I don't know if you have anything to add to that, James. I think you're more of a chemist than I am.
Yeah, I think I mean, in terms of sort of the point about models, Mike Jenkins and other guys done a lot of work on, I think, what are called structure-activity relationships. So, they will say that a particular BVOC or closed shell species, will produce, a secondary peroxy radical, i.e., a peroxy radical where the carbon is bonded to 2 further carbons, and they can say that that reacts with NO with a particular rate constant, and NO3 with another rate constant based on approximations about its structure. But as Scott was saying, the point about these mechanisms is not to get every single species correct, because they're not modeling every single species. Their point is to get the major species, the ones which control atmospheric composition, so things like ozone, OH, CO, formaldehyde, all these sorts of things correct. So in a sense, as long as we're getting most of those correct, and I'm not saying we are moving hopefully towards a better representation of them, the treatment of the intermediate species, like these peroxy radicals, is to some extent a means to an end, and shouldn't be taken too sort of, as in, we shouldn't worry too much about their precise concentrations, because they are lumped. They are a single RO2 in the model will correspond to many different RO2 in real life.
So how are the rates determined for these species? I mean, either in the MCM if they're not well known, or in CRI.
Well, there's an excellent paper from Mike Jenkins, maybe 3 years ago now, which does a lot of, essentially it's a bit of a review paper, but he brings it all together, and I'll dig it out and put it in the chat. But I think, I think it's some of the stuff that Andrea was doing, sort of, I think there's a bit of machine learning in there, probably a bit of DFT or whatever, so ab initio techniques. And then of course there was some lab-based work, lab-based stuff as well.
Okay, yeah, thanks. That answers my question very well. Great, thank you.
Thanks. Luke, you've got your hands up.
Yeah, thanks, Scott and James. Really exciting work. I was just add sort of two questions. First was, is CRI-Strat like developmental work, or is it in operate? So like, is it committed to the trunk and going to be used in UKCA? So yeah, is it CRI-Strat or Strat-Trop that's sort of preferential? And then also, I think, Scott, you said that it doesn't necessarily improve on observations. And I was just wondering if you could expand on that. And because of course, like obviously it's really cool to create these new chemistry schemes, but we also do want to simulate what's going on to closest observations. So yeah, if you could expand on why it's not reaching observations.
Okay, so the answer to your first question is yes, it's committed. It's from, let me get this right now, 11.8 I think was the bug fix, and then version 2. CRI-Strat 2, which version was that in the end, James?
It's 12.
Version 12, yeah. So from version 12, you've
okay.
got the full CRI-Strat 2. In terms of UK ESM, the vast majority of the ones going to be with UKCM 2. I think the vast majority are going to be with Strat-Trop still. And like we were kind of saying, we're not sort of advertising this as being a wholesale replacement of Strat-Trop. But I think that we're looking to do some runs with CRI-Strat. I would hope so. Anyway,
I'll be up for the
James
core
is
team.
doing some. Huh?
The core team, the Met Office for making an official release would be from them, but I guess you can turn it on. I guess, James, that's what you're doing. Yeah,
so I mean, some of the work I'm doing at the moment in my postdoc is, focusing on afforestation. So it was a bit of a no-brainer to use CRI-Strat because, we're changing BVOC emissions, and we want to get a better description of that. Yeah. But if you were, really focusing on, say, I don't know, air pollution or anthropogenic emissions, then you would, again, you probably want to think hard about it, but you probably would want to go down the line of Strat-Trop first.
Well, I mean, the regional air quality group are looking at CRI-Strat too as well, using CRI-Strat as well. And we've been working with them, like Paul Agnew and their group at the Met Office.
I've seen some preliminary results from their runs at high resolution, and their CRI compares much better to observations than Strat-Trop, where Strat-Trop just does it very badly.
So they're actually using CS2 now, are they?
I believe it was either CS2 or just CRI-Strat. I can't remember exactly which one it was, but they were doing some analysis, and it was comparing it to the existing rack chemistry that they've got, and it compared comparably with rack, but it's a bit slower, but then it has other advantages in terms of the traceability to the MCM and the fact that it's the infrastructure in the UKCA that it uses the chemical solver at the back end and those sorts of things are kind of more supported than the rack chemistry, or at least potentially more supported.
Yeah, and I think the sort of I often get myself into a bit of a like philosophical knot when trying to think of, you know, how do you say that this one model is better than another model? It's a non-trivial question. I think when I first with this evaluation that we did, we kind of tried to sort of mirror the sort of standard evaluation that StratTrop went through for Alex Archibald's paper. Well, you know, do a lot of the similar kind of analysis, and then compare using that as a baseline. Sorry, I've got builders downstairs, if you could hear that. James.
Yeah, so I mean, I don't know, I'm slightly more hard-nosed, I think, in some senses. You know, that the model is wrong for many reasons. It's wrong for its chemistry, it's wrong for its emissions, it's wrong for its dynamical scheme, it's wrong for its cloud scheme, whatever. And yeah, some things, you know, you're never going to get the right answer if you've got all of these uncertainties. In my mind, the best thing you can do is try and constrain what we can constrain. And that is, you know, we can constrain the chemistry because we have a good understanding, or an improving understanding of gas phase chemistry. In terms of, if you go and compare it to our understanding of emissions, you know, it's so much more complicated because, you know, we might say that this grid cell is 90% broadleaf evergreen trees and 10% shrub, but you know, you've got such diversity within those different, within a single type of plant functional type, you know, to get, and you know, all these things like droughts, floods, temperature, CO2, radiation, all that sort of stuff. You know, it makes calculating the emissions really difficult. So in my mind, you should always be trying to constrain what we can constrain. And I mean, a classic example is the ice screen columns that lots of groups in the US in particular love to churn out and say, oh, we've got a better ice cream emission system than previously. But of course, you're measuring ice cream columns, you're not measuring the emissions, and there's a step in between, which is the processing of chemistry, processing of the ice cream, which depends on the chemistry. So you could be getting, and then you know that leads to a back calculation of the emissions. So you could be getting, you know, with your chemistry, you could be getting a good result with your, and then you tune your emissions to do better, but actually the emissions are wrong because the chemistry is wrong. So I know I'm ranting a little bit here now, but I think improving the chemistry is a very important feature. We're not saying it's the be all and end all, but you're never going to get the right answer if you've got, you know, bad chemistry.
Did that cover all your questions, Luke, or was there an additional?
Yeah.
One?
Yeah, no, that kind of covered my question. Yeah, on obviously.
What I would say as well, in terms of UKCA CRI-2, one of the major things they're interested in there is simulated years per day. So, you know, the actual throughput of the model in terms of running. And while there might be some improvements that can be seen using, you know, from some observations from using CRI-Strat, because it's essentially a doubling of the runtime, that wouldn't win out, I suspect, in terms of the constructing it for most of the simulations when they want to run, you know, tens of thousands of model years through for the big CMIT runs. But as Scott says, you know, if you could set one model simulation up with this in, you could use that as a baseline for comparison and say, you know, this is our gold standard. But that would work, that would need to be done at some point to set that up.